Welcome back, guys. Another week. Yeah, so last week we've been trying to debug the issue where I was not able to use my Kernel properly, and I was just going through a test case where I try to debug the write to an address directly, and I made sure that this address has a memory map. This address has page table entry, and the write is not faulting, and I was able to confirm that based on logs, but still I was not able to when I tried to read from that same memory location, it wasn't working. And then I had to spend a lot of extra time to figure out this. So what was happening is this fucking, if you just let's go back to our build script, and if you look at the address, we have mentioned that everything starts from range 8 some thousand. So in our setup, the entire RAM structure starts from this actual location. So even if you write to 0000, it would actually start from 8000. So this is our 000. But what we did was we were just mapping 0x 0x FFF some 000s to 0x. This is what we mapped, and we were trying to see. I mean, like, we tried the write operation, and it was was fine. And when we tried to read from it, we didn't see anything because this was pointing to this address, and when we read from this address, there was nothing there, and it was just breaking there, and I had no freaking clue. I had to uh, go through the logs few more times to find an flash error, and that error was like a lifesaver for me because that had some different error message saying that not able to flush RAM. What's that? Flash drive. This was the error message, I guess. And when I tried to Google it, I mean, like, I was wondering why are we even writing into a flash? There's no code in my setup that writes into a flash drive because we are writing into RAM. That was my assumption. And it turns out that in QUMU setups, we are giving the starting location, so RAM starts from there. So if we are not if we are not mapping it to that starting location, because in this setup, the actual physical memory is supposed to start from here, but from my assumption, the physical memory started from 0xx0000. That was biggest blunder, I suppose, and we managed to get through it, and now we are able to make it work. And I tested it. If we get into our Kmain, this is my code now. I'm allocating memory, and it's of 16000 bytes, just to test if everything works fine. And then I just dereference it and write it directly as fork. And I also test if this byte is working because I want to check if my entire block has a page table entry. And I just typed F there, and I checked it, and I was able to read the same thing from there, and it worked perfectly. Maybe we could just try it out. What the fuck? Okay, and we tried. Yeah, starting. Let's just play it. And as you can see, the name is fork. Wait. Yes, the final parameter is this, and we are also printing. We are just printing the D. There's integer format specifier. That's why we are getting 102 here, I guess. maybe. I don't know. I'm a bit out of context at this point. Let's just check it. Hex, right? I guess hex 102. It's 66. How do we convert into its odd? There's no odds. String of length. Okay, it should be a character. Okay, then I have no freaking clue. Let's just check what's the hex of hex of this is decimal to hexadecimal. Let's try hex to decimal. No, hex to ASCII. And hex is 0x66. Maybe hex is 102. Nothing. So something's wrong. What the fuck? Wait, what's the ASCII? ASCII code. ASCII table. Where's F? Where's F? Where's F? F. EFGH. It's 106. It's oct. No, it's supposed to be 70. And hex should be. What did I type actually? We're getting 102. And what did I type? I typed F. It's lowercase f. Oh, it is correct. It's 102 f. So it is working. And even the hex is just 66. So it's working as we can see. So we have a kmalloc that can allocate random bytes and map the page table entries. And internally it's using a page allocator that's using a bitmap array to keep track of the physical memory. So we actually have a really good at least partially good kmalloc. Now we can actually try to do something with it. The thing I had in my mind when I was initially trying this out was that we need to have a user level function that does a syscall, and that syscall comes back to kernel and it allocates memory there and it sends it back to the user. This was my actual flow that I wanted to achieve. So we have a kmalloc that we can use internally, but I do have one question now. Like in Linux perspective, if user process was supposed to be allocating some memory, we use malloc. Why do we use malloc? It's just that because we don't want to keep on calling syscalls, because syscalls is a huge overhead, and if we want to allocate, if we are trying to call malloc, let's say in a tight loop, and everything is a syscall, it's just not good. That's exactly why malloc is a user level what's that, user level memory allocator. So it initially gets a huge chunk of memory and it keeps everything tracked on top of it. So we only maybe probably will do a syscall when the initial chunk is depleted. So it would be far efficient, I would say. And that's why so many exploits, user level exploits, are like dependent on the memory allocator, because in case the memory allocator has a different sense of things, about how it places objects into the memory, so certain exploits has to be exploited in a way to make use of that kernel malloc to get the exploitation work. So in our case, we are not going to write user space allocator. User space is just gonna call a syscall, and the syscall is gonna come back to kernel, and kernel is gonna do that. And I think we are going to be writing mmap, because let's just check what's the normal way to, what's the syscall that, let me just see if my recording is working. I hope it's working fine. I guess so. Yeah. What's the syscall that's used by malloc? I guess it's mmap, malloc. Instead it uses a library. Yeah, finally we'll be using mmap, and mmap is going to use to create private anonymous memory mapping. This approach allows allocate memory directly from the without modifying the data segments. Uses either, okay, for if it's a large chunk, then we use mmap. If it's a small chunk, then we just increase our current boundary with bark or spark, I guess. Because from how I remember it, so heap grows downwards, stack grows upwards, I guess. So heap, let's say heap is in this 54th line. This is the end of the heap, and if we want to increase it, spark will just increase it to, let's say, 60th line. So we have added 4 more things, something like that. I'm not exactly sure, but that's how I remember it. We could maybe see it somewhere. Yes. Oh, stack grows downwards and heap grows upwards. And let's say this is the end of the block, we just increase this even more. That's how it works, yeah. Yep, and it's really good. It's a really good way to, because we don't have to completely move things around, because as there's enough space here, we just increment the end pointer to somewhere even higher, so we can keep on allocating them. And it's so what exactly do we want to do here? I want a user space program that's gonna call a syscall, and it's going to come back to our kernel EL1. There we are gonna use, let's say, okay, let's check what kmalloc. Okay, it's the kmalloc is directly using page tables. What does mmap use? That's what we have to check. What does mmap use internally to allocate new memory? I believe it should be the same, similar to kmalloc. Uses kernel virtual management system to allocate new memory. So it is going to call kmalloc. I don't know, let's see. It's a pointer to a virtual memory, and the virtual memory is allocated, but the file is not locked. I didn't get what I wanted from this answer. Let's see. Namesh hats. Maybe does. Mm, maps files or devices into memory. What the fuck? So, how the fuck does Kemalak use this? Wait, let's just see the different. New mapping in virtual mode is off of the starting address for the new mapping is the address. Mm, Kernel will pick a nearby page boundary, create the mapping, contents of the file mapping or initialized using length bytes. So the file descriptor can be closed immediately without invalidating the mapping. Okay, so there's two ways to use this. In general, if you don't pass anything, you just get a um, size blocked at certain location. But in case you did give some address, then you are actually mapping that particular, in general maybe it's a file, into that memory, so you can access it um, whenever you want without having to do a file IO, because it's faster. I guess this is what Python libraries like NumPy and other machine learning libraries use, because they are often trying to deal with files and they don't want to do the file IO, because file IO is really costly, because we are actually trying to read something from the disk and it's going to take a lot of fucking time. So it's better to take the file and map it into memory and read it from the memory, so it's faster. But I didn't know this. I mean, I know this, but I didn't know this is exactly how it worked. That's interesting. Still, it does not answer what I'm supposed to do, because let's say let's write a small diagram of what exactly we want. Say we have a user process. Let's just create a block. We have the user process that's going to call, let's alloc mem. This is gonna be our helper. Let's say we want 300 bytes, so we do the syscall. Syscall is gonna be let's just call it a map with first argument. Let's just set it to null. Maybe we don't really have to do anything, because let's just assume that a lockmem is just going to be accessing a syscall. So let's write a syscall general helper. And it's going to be taking okay, it's going to be taking the first argument will be the syscall number. So let's assume the syscall number is 5, and the arguments will be 300. And syscall comes back to, we switch to kernel space. Let's also write restore the context, switch to kernel mode, or EL1 would be better. And then what do? We find the handler, which is going to be a syscall handler in this case. Syscall handler. Now what do? Now we are into the actual syscall. Let's say syscall. It would be, let's call it Lockman. We are here. Now what do? Now we can just call our internal kmalloc. We can write something else and keep kmalloc as something that can just kernel level functions use. So we have some sort of segregation, so that maybe there are some specific things that kernel functions do that we don't have to expose to a function code that is called from user space. So it can reduce some attack surface, something like that, but we don't have to worry about that stuff. So let's just call kmalloc here, where this function is going to just call kmalloc with the bytes. Super cool. Now we have, and this already works just fine, and we returns virtual address. It returns the virtual address. And now we restore context, and user process will get the memory, virtual memory. This is what we want to achieve. I guess we did finish a portion of this in somewhere. Let's check it. Let's keep this image. It seems useful. Let's go to my website, and I think this is where we did it, because it's a simple scheduler. I wrote a scheduling function that's going to take three, like in general I had three programs, and it's going to be switching A, B, C, and it's round robin scheduling, and things were working just fine. What did I do after that? And then I started MMU. Okay, fine. Let's go to that code then, just to get a glimpse of what was there. Maybe we could copy things from there, because we don't really have to rewrite every damn fucking thing. If we go to the k-main, let's see. Yeah, we have kernel stack, user stack, and we have two user loops, and we have a task init that's going to take a task, some ID, and some base vectors, and it's going to do some initial context things, and it's going to enqueue that task. And so we init two tasks, and we set the first one as the initial task for the scheduler, and we do what is this, DAFCLR2. Yes. During task initialization, we are supposed to mask all IRQs, because let's say you are doing some random shit here, and a random interrupt pops up. I don't think that's a good thing, because you at this point you don't have any sort of interrupt handling. So it's better to just mask it, because I believe we masked it in the start. Yeah, we mask it here. So as soon as we get into the start, we don't care about interrupts at this point. We have to mask everything, and we only start asking for our start allow interrupts to be handled by enabling this. And then I don't know why we have to start from this, but we are starting from this. I think it will work just fine, because I have tested it and it worked perfectly fine. We could also just look into the vectors, and I guess I explained everything in my article. In case you want to look into it, but I will go through it again, because I've been switching the entire blog thing into a separate session. So it would be useful if I could just go through it here. And it's just assembly that's going to store. So let's say we are in some IRQ. I guess you must have seen it in the previous session, where when something random happens, we directly fell into this IRQ, EL1 IRQ sync. I guess it's sync, not entry. Let me just remember what's the difference between sync and, let me just recall it. IRQ sync versus IRQ. What's that? IRQ sync and IRQ entry. I guess it's supposed to be for exceptions and for normal syscalls. I believe so. I must have taken some sort of notes. Did I not? That's sad. How the fuck am I supposed to recall it? I remember writing it somewhere. Let's go to any other old example and check it. Let's see the minimal boots. In kernel interrupts. I believe it should be here. Core handlers. Here it is. Not this. I believe I tried out how we can switch between different interrupts in this. I also have a user loop here. We have IRQs, and IRQ is on its own is a big mess, because we need to be. I learned that there is a what's that? There's an intermediate physical thing that's going to collect IRQs from everywhere. So because let's think of IRQs are asynchronous, because you don't know what might happen, because if you just randomly type a key in your keyboard, it's an interrupt. You are actually interrupting the CPU and saying, I have a fucking key here that's pressed, and you're supposed to do something about it. And that's not actually good, because let's say CPU is doing something interesting and you just pressed a random key, and now you just interrupted the CPU directly, and that's not good, because because that's not allowing us to bring that asynchronous the multitasking feel, because as soon as you press this, you are actually interrupting the CPU from doing its actual task. So it's better to better someone else collects all of these interrupts and store them somewhere and pass it to CPU with some priority levels. That's exactly what GIC is going to do. And when I landed, I really thought initially, as soon as some interrupt comes in, it's going to be directly handled by CPU, because that's how I designed one of my CPU, because I did design one of my CPU in my a master's degree, I guess there's some what's called switch. I guess CPUs take input in terms of switches and things, so you can just directly pass any interrupts there. And we have this reset signal, and that was the only interrupt we sent to CPU. If that is pressed, CPU is just completely restarted. And I know I have a RTL diagram where I took my interrupts high, so everything is zeros and ones, right? So you take the high of the was that my reset button and just directly connect it into my CPU's exception interrupt handler switch. I don't remember if I call it switch. What the fuck is that? Oh, wait, let's see some RTL diagrams. We should be able to recall it. And I think it's a good thing to see that. RTL diagram for simple CPU. And RTL diagrams are so fucking annoying. Let's go to image. Yes, this is the thing. It's just so fucking annoying. I was actually really bad at writing this RTL code, as you can see. So what we do is that we take these are like external things. We, let's say here there's a clear and there's a clock, and clock is going to drive the entire CPU, and there is also a reset button. So the reset is a physical device and you are pressing it, so it's going to send signals, and it's an asynchronous thing. So we pass it to a AND block, and we, what do we say, synchronize it to the clock, because at every clock we check if there's a reset and we pass it down to the control logic. Here it's ALU. I think it must be somewhere, because we do have clear here. I believe this is what I called it as reset. In this setup they have made it as clear, and it's directly sent to IR, and it is also sent to lots of other places. And this is how actual CPUs work. It's just so much RTL designs, and from what I know, I don't think nobody writes code they actually like I used to think that everything is written, but in embedded safety critical sites and inside CPU, everything is generated. It's almost everything is generated. You write the ASMs, you write the, not assembly, it's I guess it's some flowchart. I don't recall the name of it. It's ASM. You write the ASM charts and then you convert it into RTLs in some simulation software. We used something called Simlink, I guess. I don't remember, but you draw that in that. You do this same entire diagram, and it will completely generate the Verilog for you. You don't have to do anything. It will generate. And I believe for safety critical reasons, generated code is somehow good. I don't know if it's true, but based on how I remember it or how my professors told me, it's supposed to be good. And it's supposed to only, because yeah, I know, because there is only finite states, because you draw ASMs and you convert it into RTL, so you know your code is finite. You don't have infinite things. You have to show all of your possible cases, or at least you should have some sort of link to your possible states. and those states are converted into um, modules. Mm. And yeah, one more thing I learned that's completely good was the clock. Every damn thing is driven by clock, and that's why we call our CPUs as if you let's take ARM CPU, ARM M1 CPU clock speed. And it says 3.5 gigahertz. Oh, fuck me. Yeah, it says 3.2 gigahertz. That just means your clock is oscillating. It's converting up and down some billion times for one clock cycle, I guess. I guess that's how I remember it. Wait, let's just double check that. Because I don't want to give misinformation. But I definitely, because in my example cases, I was only using 50 megahertz. Yeah, max 50 megahertz. And in that 50 megahertz, there would be at least some a big log of up and downs. Up and downs, as I mean, the actual clock going high and low. That's the one cycle, I guess. I know. Let's just confirm it. What is one cycle of clock in this? And in 1 second, how many clock switches can happen? So that is 3.2 billion clock cycles per second. So we are actually sometimes I just look into my code and I wonder, it's taking, let's say, 100 milliseconds, and I would be like, it's only taking 100 milliseconds, then it must be actually really good. My code is really good. My performance is actually really good. But it's not. If you're wasting 100 milliseconds, that means uh, you have actually used, let's say, what, three is 1 second, so I guess you have at least used 3 million cycles, something like that, or 30 million, probably 30 million cycles to finish one operation. So what exactly? I believe like the code is really bad. That's why it took 30 million cycles to finish something. Or maybe it was just waiting. Probably if it was probably just doing some IO and it was just waiting. That's why most of the IO based code are asynchronous, because you are probably just waiting. Why do you want to waste your CPU cycle? Because 1 second in terms of CPU is 32 billion clock cycle. And let me just draw that. A clock, as per this here, as in this is the clock, right? It's just going to oscillate up and down. It's going to go like this. Let me draw this. You go here and we go once up, and we, how, if I could draw something in the top, it would be so much easier. We go top and then we bottom. This is one CPU cycle, and we go 0, we go top, this. So we do this what's 32 billion times in 1 second. No, 3.2 billion times in 1 second. That's how many times our cycle our CPU would just go up and down. And we have to sync everything across all our modules. If a module is not synced by a clock, that just means something is going to be wrong there, because most probably whenever I have a module that's not synced by clock, and if I take an input from that, it's a whole lot of mess. And debugging issues in this is even worse, because if you put a print message there, it's going to use some clock cycles, so you are actually making it worse, because you don't know in an actual scenario where when we will reach that particular module. And in a real debugging case where you added a print message, in that case, when how you will reach that module, it's just impossible to predict. But if that module is synced by clock, then it's fine, because you know that you are going to reach that module every time the clock is high. I guess almost everything will be in high, because simply we trap edge, nav edge, clock edge high. I guess I completely forgot everything, but I guess it's clock edge high or clock edge low, something like that. It's very lag, and it's another language that I learned. It was fucking annoying language, but it was good. That's when you will actually know that your operations like push, let's say in your assembly you type push something, the push itself is going to be implemented in Verilog, and it's a huge mess. Lately, if I have it here, github.com/Marco I don't know if I have it in public, because I do have most of my oh, I guess it's not here. Fuck it. That's sad. I think it's not here. I think it's in private, because my professors were damn sad about plagiarism, so I was not able to make my code public. Yeah, I don't have it here. But let's just take a small Verilog example. Clock counter example. Only after you knowing these stuff, you'll actually know how much slow your actual code is. It's simply so fucking slow. That's why there are some actual new research that is being done for I guess for machine learning, where you just get a new instruction. So let's say, I guess the most important operation they are going to do is matrix multiplication. So you just give a new instruction for it, and instead of writing the entire code in your C and converting it into instructions, you just have one instruction that's going to take two matrix, and it's going to multiply, and it's going to give you the output. And yeah, this is a example counter. It's just going to count numbers. So its input is a clock, and another input is a reset, and this is what I meant by the reset button. And you have output register, and you also have to give the total number. So if this is 4 bits, then I guess you have 4 some what do we say, permutations. So your code always has to start with this. At least if you're going to do something that's sync, you have to use this because you are saying always on positive edge of clock. That means whenever the clock is in the high, you get into it, you check if this code does not matter, you can just out equal to out plus 1, that's just incrementing. So at every clock high you are incrementing it. So if you run this code and if you increase this register size and if you run it for this clock thing, in 1 second you will be able to count 3.2 billion. Think about the scale. You can, in 1 second, you can count 3.2 billion. Let's try it in Python. If you write a simple counter, what can we write? Exit temp test. Let's say I equals 1, I plus plus I just have to write a loop, right? I less than, no, we just put true. We can kill it. I plus equal to 1. And let's try keyboard interrupt. Accepts exception as E, print current, and I. Hopefully this code is correct. Let's try it. It's running. Let's do a keyboard interrupt. Why is keyboard interrupt not caught? Except exception as E. I have to try keyboard interrupt. Interrupts as E. Skillets. We managed to go. Let's see. Let's time it. Because we don't know what's our actual capacity in Python 3. Time. Okay. Almost 1 second. Let's run it for 2 seconds then. In 1.8 seconds, we managed to write how much? Did it say? We managed 27 million. Oh, okay. That is a good number actually. Let's just confirm it, but I don't know if it's correct. Into words. Yeah, 28,900,000. We were only able to manage 28 mil, and my clocks, I am using M1, so my clock cycle is 3.2 billion. Think about the scale. We were only able to use 2. Maybe there's thousands of things running, so I didn't get enough CPU time. And let's say how much CPU time it actually used. I think the time will say that. I think we have used 1.2 seconds. Let's check it. How much CPU time in seconds did this process use fully the full CPU? So we did use the full CPU, full entire CPU. We were not. Maybe we did got interrupted a little bit by syscalls and stuff. Even if we assume the best case scenario, maybe let's say we should be able to reach 50 million, and the sheer amount of scale we can achieve is 33.2 billion, but we can what we have achieved is just 50 million. That's how much slow our computers are, or at least our softwares are. It's just that we don't appreciate the actual performance a CPU can give you. We just simply write random stuff on top of our um, instruction sets, and we believe that we have achieved super performance. It's just not true at all. We can achieve this much, and I guess this is also only by because there are certain things that can go wrong if you even shrink this. You can run these at higher clock speeds, but at some point you'll lose certain things, because here one clock cycle is 3.3 nanoseconds. 0.3 nanoseconds. I guess there is something called disk write speeds, where even RAM speed, if you're trying to access the RAM, there is some difference. So even if you have a clock cycle that's faster than let's say 0.1, it's not we're not actually using anything, because in that extra cycle we have used some power, but then we didn't do anything actually, because even our external RAM is still not fast enough. I guess what is the fastest RAM write speed? Read speed, right, will be hard. Read speed in terms of one clock cycle. See, even the fastest RAM would take at least 60 to 120 CPU cycles. That's why we use catch. Okay. That's why we use catch, because if something is in catch, it's just 1 or 2 cycles. We are only missing 2 clock cycles. But if you have to actually take it from the RAM, we have to wait for this many cycles. When I learned this, it was actually really mind blowing, I would say, because I didn't know any of this, and when I learned this, it was just completely new and completely amazing. And that's when I understood that everything we write on top of an instruction set is already slow. It's already fucking slow. Anything we write on top of an instruction set is slow. I think Risk is trying to improve things. I don't know. Risk architecture is trying to improve things, I guess. I believe. I don't know. Maybe. Yep. Yeah, well, let's get back to our initial conversation. Where were we? Yeah, IRQ versus IRQ entry. This is what we wanted to do, and somehow yeah, that's how we ended up somewhere else. Let me just see what's the difference between the actual question we had, that is IRQ sync versus IRQ entry. I don't know at this point. I'm supposed to know because I have written so much fucking code for it. I guess we could just ask this fucking thing. Difference between IIQ sync versus IRQ entry in ARM. Or did I name it myself? I don't think I named it myself. Ah, I remember something like a CPU exception. Yeah, IIQ sync is like what's it? Interrupt state returning from an interrupt context, but here we are returning is getting into interrupt context safely, and IIQ sync is what? Is about correctness between IRQ enable and disable paths. What does that even mean? IRQ purpose interrupts context synchronize IRQ states timing at IRQ arrival after mask. Maybe it's fucking with me. I think it is hallucinating, or maybe it's interpreting my question completely differently. Let's just go into my context and see examples because I must have added it somewhere. If not, I must be so damn. I think I did because I know I somewhere documented it because if not, I wouldn't be able to recall everything. I don't see it. Where the fuck is it? What? No, 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 no. I don't have it. But I remember writing it somewhere. Because initially, when I was trying to write this, I had the same question. I did all the fucking stuff to. I understood this part because there are different things because there are 4 slots and every slot can have its own IRQ sync and IRQ sync. Maybe if we copy paste this fucking thing, maybe it will be able to understand it better. Why did I not? Why did I not document it? I should have documented it. Synchronous exception and IIQ's asynchronous interrupt. Yes, yes, yes. When CPU executed instruction and that requires attention, that would be the syscalls and break and stuff like that. And if you have some page faults, instructions, divide by zero errors, and that's what we call it as synchronous errors because the CPU is executing somewhere and it has interrupted and it has come into some interrupt handler, and that's what it means as synchronous. And we have the asynchronous interrupts, and that's just anything. That could be anything. That's just timer interrupt, because timers, as I said, clock drives the entire CPU. So it needs timers, and every time the clock ticks, you actually get a timer interrupt. And that is what we have it as a separate handler, and we this is the timer handler. We have IIQ, and this is just going to call the timer interrupt. So every time, yeah, this is one of the thing that I wanted to see. Even our kernels don't always run on the same clock cycle as your CPU. Your kernel might also do some sampling. So as you can see, I have a handler here that's going to take something, and it's going to mask something, and it's going to figure out that is this a timer handler or not, and timer interrupt or not. And what is a timer interrupt? Timer interrupts is actual tick. So every single tick, every single up signal, that's what I mean, like this. So this is a timer interrupt. Whenever we have an up, we come here. So even this is not really good for our kernel. If this happens all the time, what exactly will our CPU actually perform? Because in every CPU high, we are actually trying to do an interrupt, and what's the point? There's going to be no real work done. And that's why within the handler we sample it. And in my case, I sampled it till 1000, and then I printed it. I guess when I was trying to do this, I think I checked it, and kernel samples it to a certain number, and then uh, considers that the clock has changed from 1 to 2. It won't consider it to be changed to 2 as soon as we get a IRQ, timer IRQ. And yeah, once even more worse is network card, because network cards will just throw interrupts at you. Every time some packet arrives at your network card, it's going to rise an interrupt. So if you think about that, your CPU is it's always in DDoS mode, because packets are, even if you're in a simple local network, packets are being thrown at you at scale. But still there is a nuance where and right now network cards simply don't throw an interrupt as soon as it takes as soon as it gets an packet. It's going to keep those packets into a buffer, and once the buffer is full, it will say that my buffer is full, please fucking take it, because I won't be able to get new packets anymore, something like that. Yeah, the fucking internals of CPU was just so much interesting. Every time I get into something, I end up understanding. I end up trying to learn something new that is completely new. I mean, like, I would not even have thought about it, but and that would be there, because this Linux kernel code has been there for like 30 years. I don't think anything can be found new. Almost every problem has been probably already been solved. Right now, the new things are probably just the scaling factors, probably new features. It's not there's no fundamental problem that needs to be taken care of. There's only scaling problems, there's only security problems. Those are the things that has been addressed at this point. Okay, I'm talking a lot instead of writing fucking codes. Yeah, so we know what an sync is, what an IRQ is. This is a important thing. There's also fast interrupt. What is fast interrupt? Do I remember what's a fast interrupt? Okay, it's for unused. Yeah, probably that's why I have for every as my code. Where is my vector? Vector. Yeah, it's here. Yeah, for every level I have 4 interrupts, and the last two ones are not handled. The first two I have separate handlers, and the handler code is also almost always the same. We just save the context, we move some parameters for the function that is the handler that is about to call, and we call it and we get the output from it and we save it and we restore the context, and it's going to be same for almost every entry, and we have to keep this as simple as possible because this is performance critical. Because if you are going to do some sleep inside a interrupt, you are just wasting CPU. Save context and restore context is also pretty simple. You just save every register into somewhere and you restore it. Nothing much. Save every registers and also maybe some special registers like where was the stack pointer and what was the ELR one. I guess this is the page table, and this is the flags. Yeah, that is all. We don't have to do anything. A context switch is technically this, nothing much. You just take the registers, so save them, and you take the important special registers and you save them. That's it. And when you return, you pop everything into the certain things, and so you are back to this previous context. And it's that simple. Okay, where were we? Where did we leave off? I think we were here. I guess we wrote some. I guess it's here. Yeah. I think we have a small understanding of we need a user process that is going to be scheduled, and that scheduled process is going to call a syscall, and the syscall is going to be a lockmem, and it's going to give us some bytes that it wants to allocate, and internally it's going to be a syscall with a syscall number and the input, and we get in because this is a syscall, we are going to be inside syscall el0 sync because we are from el0. I think it should be here. Yeah, I'm just using el1 because I don't have a different handler. And where's my code? Yeah, and we store the context, we switch to el1, we find the handler, and within that handler we have to write some syscall actual mapping, because as you can see here we say that it's a syscall and we say it's a fifth syscall. I have just randomly taken it as 5. So within the syscall handler we have to have some switch statement which is going to switch through different numbers, and if it's 5 we have to assign it to this syscall allocmem, and it's going to internally call the kmalloc. I think I have already done that part to somewhere. Let's see. I think it's supposed to be in this code. I don't know. but somewhere I did it. Mhm. This was really fucking interesting code. I guess it's a linked list, and I fucked up big time there. Figuring out that part was so much harder. I don't have it. No, I know it's somewhere. Syscall. Ah, it's here. The Syscall dispatcher. Syscall dispatcher does not have anything. Syscall dispatcher. I think I changed it. But it's, yeah, as I said, it's just going to be a simple code where we use switch statement. Let's see if I have switch statement somewhere. No, I don't have any switch statements. Probably I must have removed that code because as I said, it's just going to be switch statement with multiple um, multiple things, and it's just going to switch into Z5 different syscall numbers, and it's going to call the thing. I guess that's about it. That's about the theory, and that's about the thing that we need to achieve. That's this. I think I talked a lot. Let's just implement this. Yeah, I guess we'll implement this in the next session, but this is a quick theory of what we want to achieve, and it would be a good thing to start it in a fresh session so we'll have the cognitive ability to do it. Thank you guys. Have a good day. Bye.